Hello, everyone, and welcome to this OCP educational webinar titled Compact Thermal Management Solutions for High-Density AI Data Centers. My name is James Kelly. I'm the VP Market Intelligence and Innovation here at OCP. Thanks so much for joining us. As people are inevitably joining right now, as the webinar is set to begin, I will just open up with some quick housekeeping items. One of the great things about these OCP webinars is that you have the ability to ask questions and get answers live at the end of this webinar. So you'll notice that there's a Q&A box. If you've got a question about something that you're seeing or hearing during the webinar, please do at any point drop a question in there and we will get to them at the end. We usually leave the last 10 minutes or so of the hour for questions and answers. You can also wait until then. Stay tuned for a poll question as well and vote for that. And with that, I think that, as always, people do ask about if the slides are going to be available. Is this going to be available on demand? As always, yes, you'll find that on the OCP website afterwards. So I think that about covers it for the housekeeping items. And I see plenty of people have just joined now. So let's get started again with this webinar titled Compact Thermal Management Solutions for High-Density AI Data Centers. There's plenty going on when it comes to high-density and cooling environments within the OCP, of course. AI driving compute memory densities, and with that, the need for more power, generating more heat, and the need for more cooling. So getting those cooling, particularly when it comes to direct-to-chip cooling, equipment that we'll be discussing today into the servers and the systems in a compact way so that we can keep the systems rack dense and have all that compute close together, especially in the scale-up environment, is increasingly a challenge. In particular with all of the functional and non-functional requirements of that, like all of the reliability, for example, that goes along with it. So that's exactly what you're going to be learning about today. And joining me today, we have our sponsors, two people from our sponsor, Parker. We've got Elvis and Josh. Elvis is the new product development engineer at Parker. Josh Koh is the market manager at Parker. And as always, we've got an analyst. In this particular time, we've got Yulin Wang, the senior technology analyst at ID TechX, that's going to open up the webinar, our first section of the webinar, and close us out with a few concluding remarks. This is a quick look at the agenda. Yulin will be kicking us off with that first section, and the next three sections will be divided between Josh and Elvis at Parker. We'll throw it back to Yulin for key takeaways, and then, like I said, the last 10 minutes Q&A, so please ask your questions in there. And stay tuned for a poll question after our first section. So with that, I will hand it over to Yulin to take us away at this very first section of the agenda.
Great. Awesome. Thanks, James. So hello, everyone. My name is Yulin, and I'm from ID TechX. So the first part of our agenda is to understand fluid transfer systems for data centers. So when we talk about the liquid cooling in data centers, so essentially the liquid cooling happens on two different levels within the data centers. So if you can draw attention to the left-hand side of the chart, the first part where we see liquid coming into the data center is on the server and rack level. So essentially there will be some server and rack level cooling, and specifically, traditionally we have air cooling, typically using fans. So when you buy servers from the server OEMs, you will see a lot of fans installed on those servers directly. So that's the traditional way. And then what we are seeing for AI chips or AI server boards is that people are transitioning to direct chip cooling, or also known as cold plate cooling. And within this subcategory, we have a single phase cold plate and two phase cold plate. And the differentiation is, whether there's phase change of the coolant inside of the cold plate. For single phase cold plate, typically people use water glycol PG25, and for two phase cold plate, typically people just use some sort of like a dielectric liquid. And then moving to the next generation, potentially, and a lot of people are exploring right now, is immersion cooling. So similar to DUC cooling, depending on whether there is phase change of the immersion fluid, we can also split into single phase / one peak immersion or two peak immersion. So that's what happens on the server and rack level cooling. And on the right-hand side, we have the room and the facility level cooling. So a lot of data centers, as of today, still rely on air cooling. So you will see the computer room air conditioning or computer room air. So those are pretty common. However, for data centers, many data center owners are increasingly transitioning to liquid facility water systems, data center real estate. So that's the trend we're seeing. And then finally, in the future, some people are also exploring, introducing refrigerant into their room and facility level. However, this is a relatively novel concept, and personally, I haven't seen any like a large-scale commercial adoption of this facility level. And then we, match server and rack level cooling with room and facility level cooling together. So traditionally, we have air-to-air. Don't really make any changes on the facilities, but they can make changes on the server racks. So that's why you will see liquid cooling on the servers, but air cooling on the facilities. New build data centers, a lot of people are transitioning to liquid. That means liquid cooling on the servers and liquid cooling on the facilities. So this slide essentially shows the thermal design power trend of GPUs. Thermal management in AI data centers is actually driven by the TDP of GPUs. Typically, the TDP of CPU is much lower than GPU. So that's why, on this slide, we only focus on GPUs. So the chart on the right-hand side summarized the TDP of data center GPUs over the past 8 years, all the way from 2017 to where we are now, 2025. So if you look at, Nvidia's B200, and if you look at AMD's MI350, released several weeks ago, then we're looking at, the TDP of 1,400 watts. So then what is the timeline and what is going to happen with the ever increasing TDP? By directly interviewing quite a few chip manufacturers, I think the consensus is that, when the thermal design power of chip which is between 1,500 watt and 2,000 watt. That is where, when the TDP falls in this interval, single-phase direct-to-chip cooling will definitely struggle to meet the requirement. So, which means, people kind of have to transition. It's the critical timeline for the transition of two-phase direct-to-chip cooling. Including the technical challenges, commercial challenges, as well as some notes on the side. There are several technical challenges, for example, the leakage of the coolant and the risks of IT equipment, therefore requiring, a very comprehensive maintenance over time, because, water glycol is used inside of the cold plates. So if there is any potential leakage, risking your server boards, which are worth, hundreds of thousands of dollars. It's pretty easy to understand. High mechanical stress due to the high flow rate per minute. So just to give you some numbers, if you want to cool down a chip with a TDP of 1,000 watts, then typically you're looking at somewhere between 1.5 and 2 liter per minute. Results in a significant pressure from the quick disconnect, which is a huge challenge that people have to consider, when designing the server racks and data center many cold plates, which leads to the replacement difficulty and also relatively high capital cost.
Can I interrupt you for 1 second? There's a few people that are saying your audio is cutting in and out, which it seems to be for me too. Maybe just try turning off your video and use your bandwidth for the audio so we can at least hear you. Thank you. Sorry about that, folks. Okay, go ahead.
So, and another challenge is the IT and facility lifecycle mismatch. So typically the life cycle for IT equipment is somewhere between 3 and 5 years, whereas the facility life cycle is usually like a decade or two or longer. So, the challenge comes through when people want to upgrade their IT equipment, then, how to make sure the new IT equipment are compatible with the old facilities. And also high maintenance over time, which reflects the first technical challenge that I mentioned just now. And then moving down to two-phase D2C, the technical challenges include, the upfront system cost, managing flow and pressure across cold plate, and the lack of technical expertise. In this particular area, because two-phase D2C is still a relatively novel concept, and also health and environmental concerns like the PFAS and the global warming potential. Global warming potential is less of a concern because there are quite a few refrigerants with GWP around 1 or less than 1, so that's not too bad at the moment. And then in terms of commercial challenges, complexity of the initial system design and high capital cost. So two-phase D2C cooling, the capital cost of two-phase D2C is typically 20% higher in comparison with the single-phase D2C. And also the refrigerant supply and how to recycle the refrigerant is also a challenge, and there is no industry standard to my best knowledge at the moment. And this slide essentially shows an overview of the single and the two-phase immersion cooling. But this presentation will be primarily focusing on direct-to-chip cooling. So I will quickly, skim through this slide and then jump to the next one, just in the interest of time. So for immersion cooling, there are several similar challenges. The first one is complexity of retrofitting, because the principle of immersion cooling is very different from using server racks. So essentially, you need massive immersion tanks and a lot of coolant inside of the tanks, which is quite heavy. So that essentially puts a lot of pressure on the floors of your data center IT rooms. So that essentially means you have to do a lot of retrofitting to make sure that your IT rooms are compatible with the heavy immersion cooling tanks. And that also leads to a very high cost and some potential technical challenges in terms of fitting the server boards into the immersion coolant, and a very comprehensive material compatibility testing is often required. And for two-phase immersion cooling, one worth noting challenge here is the regulations. So far, for the majority or for almost all the two-phase immersion coolant, there are some like a PFAS regulatory concerns, and because of this regulatory concern, a lot of people are thinking of transitioning from two-phase immersion back to single-phase immersion. A lot of companies that I have spoken to, they have trialed two-phase immersion, but due to this regulatory uncertainties, they're thinking of going back to single-phase immersion or even two-phase direct-to-chip. So this slide is a quick overview of the market size and the commercial trends of the data center cooling components. So essentially, here we are on the right-hand side, we have the market size of different components all the way from cold plate systems, quick disconnect, air cooling systems, and all the way down to CDUs and pipings, valves, and monitoring. So, with the rapid expansion of data centers and artificial intelligence, we believe that, liquid cooling components will experience a very fast growth. So for the next 5 years, we believe that there is a 25% compound annual growth rate, which essentially represents a, pretty, fast increase in this entire market. And in 2028, we believe that the market size for all of those components, on this slide, will reach around $15 billion. So one of the significant challenge that is worth noting is the retrofitting and energy efficiency, because as liquid cooling adoption accelerates, retrofitting existing infrastructure has a significant challenge, particularly in maintaining energy efficiency and also space-saving fluid transfer products become essential in optimizing thermal performance within the constrained data center layouts. So with that, we're going to discuss their products and solutions on thermal management for AI data centers. Thank you.
So I'm going to take it back actually for a quick poll question here. Everybody can weigh in and vote here. As you can see, the question is, what do you see as the timeline for significant adoption of single-phase liquid cooling? Would it be A, within the next 6 months, or 6 months to 2 years, 2 to 5 years, or even beyond that? Yeah, please cast your vote, and we'll give people a few seconds here to do so. I see some votes slowly coming in. We've got plenty of attendees, hundreds of attendees here on the line, so hopefully we get a lot of you weighing in on this. Obviously, the timeline for this is faced with the challenges that Yulin was just talking about, right? So let's see. Okay, we've got well over 100 or so people voting now, so that's great. Let me advance to C. Yeah, that's probably not too surprising to me. 6 months to 2 years. Does that make sense to you, Yulin?
Yeah, it definitely does. Yeah, I think single-phase liquid cooling is already accelerating. So I would say, definitely people are seeing a, very fast adoption, at a large commercial scale. So 6 months, 2 years, sounds very reasonable to me.
Yeah, lines up with your market growth forecast. Okay, let's hand it over to the folks from Parker now for our next section.
All right. Hello, everyone. How's it going? During this presentation, we're going to focus on a component view for data center cooling strategies and focus mainly on the 3 highlighted topics. So we're going to be talking about how do you maximize your energy usage efficiency while also keeping in mind your space constraints and ability to troubleshoot and maintain your systems. And an easy way to quantify your effectiveness or your energy efficiency in your systems is by looking at the PUE of your system, so power usage efficiency, effectiveness. The industry average for a PUE for data centers has remained relatively stable in the recent years, hovering around that 1.55, with ideal goal in mind being a 1. And we can see that larger data centers get closer to that 1.3. But as we move forward and transition from air cooling to liquid cooling, we all have the opportunity to focus more at getting as close as possible to that 1 PUE. On the next slide, we're going to look at a high-level overview at what a direct-to-chip liquid cooling data center looks like. So for a typical data center for direct-to-chip liquid cooling, we can separate it into like 3 different levels. So the first level is the server blade level, where your heat exchanger is, or your cold plate, as more widely known. So this is where your heat is going to get created. And then you have your IT rack level. So this is where your pump, your CDU is going to be at, which pumps the fluid to the cold plate itself in order to get that heat out. So that heat will come from this server blade. It will go into this rack manifold. So it will go into this outlet and then back into your CDU, where at the CDU, the heat comes out of your building. So you can separate data center facility to 3 levels: server blade level, IT rack level, and data center facility level. And you have to look at the PUE for all 3 of these levels in order for you to better understand where you are having efficiency losses. And then this is just a high-level look at what are the main components, very high level, and what all goes into it. And this shows different configurations that you can have for your data center facilities. So right now, even though we're seeing liquid cooling, it is not necessarily 100% liquid cooling, even though there's a lot of people going to that. These are a lot of the systems right now are hybrid systems, which use air and liquid cooling to cool different areas at your server blade. On the next slide, we're going to look at the same visual, but for a 2-phase liquid cooling side of things. And as you can see, when you look at it at a very high level, these systems look very similar. But later on, we're going to look at these more in depth at the component level, and we're going to see how, even though these components might serve the same function, they might look the same at a high level, depending on the media and depending on how you design your systems, these picking the correct components becomes very, very important at getting that PUE number as close as possible to 1. On the next slide, we wanted to show a little more zoomed in version of that IT rack level and all the components that would go typically in it. So you can start with your CDU, where your condenser is going to be, where your reservoir is going to be, where your pump is going to be. And the way that these systems work, because they're all liquid cooled, direct-to-chip liquid cooling, is your pump is going to be pumping your coolant or your media, whether that be PG25 water or refrigerant, is going to be pumping it through a filter to keep the media clean. It's going to be pumping it through a manifold that spreads it into your server blades. And then as the liquid goes into that server blade, it will go through your cold plate, it will take the heat out, and then come outside. And throughout the paths, all the paths in the systems, you need to have methods of controlling your fluid and being able to know what your fluid media is doing. So you need all these components, such as like flow regulators, ball valves, quick disconnects, pressure controls, and everything else. On the next slide, it's a similar look at it, but it's for a two-phase system. So for a two-phase system, the components still remain relatively the same at a high level, but later on, we're going to look at them more in depth and see what the difference are between the single-phase components and two-phase components. The next slide that we're going to look at is what does the server blade look like? This is one of the most important parts of your systems. So in your server blade, you're going to see on your main side, you're going to have your inlet QD, so your quick disconnects is going to bring your fluid in. You're going to have some type of a rubber hose, thermoplastic tubing, stainless steel tubing, copper tube, whatever fluid transfer method that you want to do. And then you're going to have your cold plate. And then your cold plate is going to have fittings in order to connect to the tube or the hose or the fluid transfer tubes. And then usually this is what a normal server blade level looks right now. With new AI server blade levels, you can imagine that these cold plates, there's going to be a lot more of these. It could be upwards to 6 of these cold plates are going to be separated into other GPUs. But we're going to talk about each of these components later on our design strategy slides, and we're going to focus on how do you best pick and size and look at the key requirements for all of these components so that you can have the most efficient system possible. And the next slide is going to be the same server diagram, but looking at a two-phase system. And the main difference here is going to be that on the two-phase side, as Yulin mentioned, flow rate control becomes much more important. So you're going to have a flow regulator in line with your cold plate in order to prevent dry out here, because your media is going to start switching phase from liquid to vapor. And then, sorry about that. Then I'm going to hand it over to Josh, and Josh is going to talk to you guys a little bit more about how do we approach pressure drop minimization. And then later on, we're going to focus at all these components that we just saw in a more in-depth level. So Josh, you can take it over.
Thanks, Ellis. Yeah, as Ellis kind of mentioned, I want to start to talk about pressure drop minimization within a system. So there's 3 key areas that I'm going to talk about. So sources of pressure drop, where those things can come from, strategies for minimizing those areas of pressure drop, and then the benefits that come from minimizing those pressure drops in those areas. So the 4 key focus areas that I'm going to discuss today are going to just be hose and tubing offerings, fittings and connectors, manifolds, and then system flow restrictions that could be sources of pressure drop. So strategies to minimize pressure drop within those applications is just going to be optimize hose and tubing sizing. So appropriately sized hoses and tubes that have adequate flow rates with minimal resistance, using a streamlined design. So engineering these systems with fewer bends and restrictions to make sure that you do have great coolant flow within those systems. Then using high quality components, using low resistance fittings, good connectors that minimize turbulence and pressure loss within your system. And then, implementing some sort of routine check for regular maintenance in these applications with products that allow for that. So again, things like quick disconnects and proper routings can go a long way in routine maintenance. So benefits that are going to come from some of these areas of improvement are just going to be increased efficiency overall within your system. So you reduce the amount of pressure drop, you're going to have a lot less energy consumption within your pumps, and you're going to have overall system efficiency gains that you see. So you're also going to see improved cooling performance. It's going to have constant flow rates. You're going to have your critical components online, and they're going to be at optimal operating temperatures for you. So maintaining those optimal operating temperatures is also going to come to the last point that I wanted to emphasize here, is just extended equipment lifespan. So maintaining that temperature, operating temperature within your system, is going to make things like your pumps work a little bit less and extend the equipment lifespan that you have there. So this next slide is a pressure drop simulation that we conducted. So this just details how different materials and how different configurations can kind of interact with each other, whether it's in a positive manner or in a negative manner in some areas, in increasing and or adding to pressure drop within your system. So this simulation is it used Dow Frost PG30. The information that you're provided here is 1 and 5 liters per minute, and a simple S routing that you would see in a lot of these different configurations. So this just shows how different material types and how different connection types, in some cases more importantly, can impact the pressure drop within your system. So key factors in this simulation are just going to be the connection and component types that you choose, things that are optimized for this space, static pressure areas that you kind of see in the diagram on the right area there, and then making sure that these products are produced for this routing and specifically for the space requirements that you have. So reducing complexity within these systems can go a long way in reducing the amount of pressure drop within your system, and using high quality components in those areas can really contribute to significant areas of improvement in pressure drop. The next slide is just 5 keys that we will take a look at for space constrained areas. So the first thing that we wanted to talk about is just component size and configuration. You do not have a lot of space in any of these rack manifolds. As Elvis kind of mentioned, we're adding more cold plates to them every day. Number 2, you also have a lot of inefficiencies within those designs. So you require specific physical space for these liquid cooling applications that just doesn't exist right now. You also have concentrated heat loads within these spaces. So limited space, you have products that are getting hot and staying hot, and you need to be able to maintain those as for number 4 there. So you have to be able to access them. It's cramped conditions. It's very difficult to reach in many cases. So you need products that are going to optimize this solution for you. Then you have to think about cable management. All the other components that come together in this space, those have to be a requirement in your engineering resources as well. The next slide is simply just reliability and maintenance. So a couple of things that I've already mentioned. Reliability is also obviously crucial within these applications, and there's 2 main challenges and concerns in these areas. So reliability of the components, they're hot, they're in this area. It is going to lead to reliability issues if you do not have proper products that are designed for this space. So you want reliable liquid cooling products with so many different products working together in these areas, and you need to be able to design these configurations with these products in mind to be able to maintain them. So that just goes over to the maintenance challenges area here. You need to be able to service them. You need to have products that are in there that are able to be hot swapped and ideal for the working conditions that you're given here. I'm going to turn it back over now to Elvis to talk about some of the design strategies that we discussed.
So when looking at the design strategies, we're going to get a more in-depth look at the component view individually. And for the purpose of this presentation, we're going to focus on components that we as Parker manufacture and we feel comfortable talking to you guys about with confidence. So the first one we're going to focus on is one of the main components you're going to see when you enter a data center facility that is liquid cooled. And that's going to be your hoses and your tubing. These will provide the routing for all of your fluid media and do all your fluid transfer. So one of the first key things to focus on when you're looking at the hoses is going to be your sizing consideration. So when you're looking at picking a hose, you got to make sure that your hose is not going to negatively affect your flow, the flow of your media, and it's not going to introduce unnecessary pressure drop or unnecessarily increase or reduce the speed of your fluid. For example, that becomes very important when you're looking at a single phase directed chip system that increasing the speed unnecessarily of the fluid going into your cold plate is going to give you worse thermal performance. It's going to be worse at taking that heat out. Another thing to focus on when you're looking at trying to pick which hose you're going to pick for which application, you're going to be looking at these two categories that are very intertwined with together, and that is the force to bend and your bend radius. You got to make sure that the hose or the tubing you are picking can be easily routed and will serve the purpose of what you're trying to accomplish. So if you are trying to go hard tube, for example, hard stainless steel tube throughout your whole system, but you do not have the space requirement, you will not be able to make those bend radiuses work that are required with hard tubing. On the other side, when you're looking at hoses, you got to worry a lot about your force to bend, because you cannot over bend these hoses and create kinking and damage the hose. Another very important thing when you're looking at the hose or tubing is the compatibility with the fluid media or the coolant that goes through it. So when you're looking for compatibility, you got to make sure that you know very well what type of media is going through your hoses or your tubing in order to prevent contaminants from going into your system from the outside, or to prevent your hose or your tubing from disintegrating because you have the wrong media going through it, and then you get debris or inhibitors going into your cold plate within your system. Another very important thing to focus on with hoses is your end connection. So whenever you're sizing a hose up, you have the right ID, you know your bend radius is going to work for you, it's compatible with your refrigerant or your water. You want to look at your end connections. How is this hose going to terminate? And that becomes very important because there's different end connections and different terminations that become very important when you're looking at what are you trying to achieve with this hose. And if, for example, if you're trying to make a hose that you're able to quickly connect and disconnect, you might want to look at your end connections being quick disconnect couplings. But if you're trying to look for a hose termination that is going to give you incredibly good reliability and leak-free for long periods of time, then you want to do a hard threaded connection with seals and gaskets that are appropriate for it. The next component that we're going to be talking about are the quick disconnects. The quick disconnects are one of the other major components that you're going to be looking at when you look at a data center for liquid cooling. The quick disconnects are an easy way for you to reliably maintain your systems. So quick disconnects, their primary function is being used to hot swap server blades in and out. And they come in all different types of end connections. But one of the major things that you want to focus on when you're picking your quick disconnects is your pressure drop versus your flow rate performance of your quick disconnect. For example, when you are building a two-phase system with refrigerant going through it, pressure drop at the cold plate level becomes very important for you to maintain and control that flow rate. So you don't want to make sure that you're putting the wrong quick disconnect in there and introducing an unnecessary pressure drop just because the quick disconnect is easy to connect and disconnect. The other thing that you want to look at with quick disconnects is your compatibility and testing requirements. So for example, if you're trying to use single phase quick disconnects with refrigerants, you got to worry a lot about your pressure requirements, right? Refrigerant has much higher pressure ratings. So some of the refrigerants that are being used in pump two-phase systems, they can go up to 200 psi, and most single-phase couplings are not made to handle or work or be able to quickly connect and disconnect at those pressures. The internal seals for single-phase PG25 water glycol are different than when you're looking at the seal materials for refrigerant use. So you got to make sure you're always worrying about the compatibility and testing requirements for all of these quick disconnects. On the next slide that we're going to talk about are fittings. So whether that be the end connections on your hoses or your tubings, or however you're going to do a connection between point A and point B on your system, you're going to use some sort of fitting. Fittings are very similar to valves or quick disconnects when you're looking at in a way, but the only difference is that there's nothing inside. There's no valve function inside the fitting itself in most cases. So when you're looking at fittings, you want to look at your flow versus your compactness requirements. So you want to make sure you're picking your fitting correctly to give you the correct flow and not introduce unnecessary pressure drop, but you also got to make sure that that fitting is going to fit inside your space requirements. And that's a very important key feature of this. And then another thing with fittings that you want to worry about is ease of use and ease of installations. When you're designing these systems, usually you're doing it in the CAD. Fittings just assemble together correctly in CAD, but when you're looking at it in a real life application, you won't be able to turn it, you won't be able to thread it correctly. So sometimes in an application, you want to use a fitting that has a swivel end connection that will make it easier for you to install in place. And then another thing, just like with all the other components, is leak prevention and reliability. You got to make sure that your fittings have the right end connection and have the correct seals in them to connect from point A to point B, so that you're not causing unnecessary leaks in your system. And then just like with all the other components, compatibility with the fluid and the media that's going through the fittings is very important. You got to make sure that you're picking the correct fitting for the correct media type going through that. Because if we're looking at water glycol systems, if you pick fitting like a steel material fitting, you're going to have a lot of corrosion issues, and you're going to have a lot of issues with the performance of that fitting. On our next design strategies, we're going to focus a little bit about talking about valves. And valves is a very generic term. It can mean a lot of different components, and quick disconnects are typically valves as well. So when you're looking at valves, you think about your pressure relief valves, think about your ball valves, electronic ball valves. One of the main things that you're looking at when you're picking a valve is your flow versus pressure drop requirements. You got to make sure every time you use a valve, there's internal components that are going to create a pressure drop, and you got to make sure you're sizing that component correctly, and that you have to be sure that you are good with that pressure drop that's going to be induced into your system because of this valve, and make sure that the benefit that the valve is giving you outweighs that pressure drop that you're creating. And then just like with all the other components, you want to look at your end connections. You got to make sure your end connections are appropriate for your system, and they're giving you that leak-free seal. And then you also got to look at the compatibility with the coolant and with the materials going inside the valve, just like with all the other components. On the next one, we're going to talk a little bit about is the manifolds. The manifolds are a big component of every rack or every data center system. And one of the main things you want to focus with your manifolds is your size for your flow requirement. Your manifolds cannot be too big, because then they won't fit inside the IT rack, and they cannot be too small because they will not give you the adequate flow performance that you are looking at. So when looking for manifolds, you got to make sure that your sizing is appropriate, and it's going to be the first thing that comes to mind. And then the other thing that needs to come to mind when you're thinking about manifolds is your end connections, is how are all of your fittings or all your quick disconnects going to connect to this manifold. And you got to make sure you don't have any compatibility issues, or you don't have any leak issues with what you're trying to connect to the manifolds. And then looking at the manifold itself, you also got to make sure, just like with all the other components, you got to make sure that the material that the manifold is made out of is compatible with the media and the fluid that's going through it, so that you don't have corrosion issues or introducing unnecessary inhibitors into your system. On the next slide, we're going to finally talk a little bit about the medias themselves. So with the purpose of this presentation, the main two medias that we're looking at is PG25 water glycol, or single phase fluids, and two phase fluids, which it can be different types of refrigerants. When you're looking at water glycols, one of the main things that you gotta make sure you keep in mind is water glycol is very corrosive. You got to make sure you're picking the correct material. So you got to make sure your quick disconnects are stainless steel. Your manifolds are going to be stainless steel on most cases. And you got to make sure, the other thing that you got to make sure when you're looking at water glycol is your monitoring of the fluid life itself throughout the life of the system. One of the main things that comes out with water glycol is bacterial growth or inhibitor growth. So you got to make sure you're always monitoring, you're making sure that you're sizing your system, and you're thinking about the longevity of the system and how this fluid is going to act throughout the life of the system, and how you're going to clean it, how you're going to maintain it. You got to make sure you have the correct filters in there for the type of fluid you have. When you're looking at refrigerants on the other side, you don't have to worry as much about maintenance of refrigerants, but you have to worry about the high pressure that comes with refrigerants. So you got to make sure you're sizing your components correctly so that they can handle that high pressure. For example, a single-phase cold plate does not need to handle that high of a pressure, so it can be very thin. So your delta T between your cold plate and your heat source can be very small. But with refrigerants, you got to make sure that you are designing your cold plate correctly, because if you're using a 200 psi refrigerant, you got to make sure that your cold plate is going to be able to withstand that at its burst pressure. And then on the next slide, I wanted to touch on just a little bit on the other components that we as Parker do not work on, but are main components in these directed chip systems, and that is the pump and the cold plate. In an ideal world, an ideal situation, you would have your pump right next to your cold plate. These would be the two main components that you would need in order to make your loop work. And all the other components that we just talked about are the in-betweens between these two that we need in real life to make these systems actually work and be able to maintain these systems and be able to get readings out of these systems. So when you're looking at your system, you always got to make sure that your pump and your cold plate are going to be your two main focus at the beginning. And you got to make sure that you're getting the most effectiveness or usage out of your pump and your cold plate. And then you can think about all the other components that go in between that are going to introduce inefficiencies. And you got to make sure that when you're picking those components that you are thinking about how are these components going to help me and get efficiency out of these two and not introduce multiple unnecessary efficiencies. And now I'm going to hand it over to Josh to talk about some real world case studies that we at Parker have gone through.
Thanks, Ellen. Yeah, so, you're assigned a task, you go into these applications, and you are tasked with making sure that things are cool. Why does any of this matter? So we have a couple of real-world case studies just to pull all this information together, just to show you how taking design optimization, some of the strategies that Elvis kind of covered, and products that are specifically created for this space can optimize your liquid cooling loop. So the first case study that we're seeing here is a hyperscaler just looking to reduce the pressure drop and overall performance of a system that they had installed. So taking a look at that, we're able to take a look at things like hose routings, connection points, again, products not optimized for this space as contributing factors to inefficiencies within the system. So working with this hyperscaler, we were able to optimize hose and tubing diameter offerings for maximum flow and aid in their routing process with things like quick disconnects and minimizing the effort that's added there. So this second case study that we have here is just going to be a quick disconnect optimization case study that was just a data center operator looking for improved reliability and efficiency within a system that they had. So implementing quick disconnect fitting offerings with designs that are OCP inspired designs with superior sealing capabilities obviously improve the overall system efficiencies and reduce the downtime for maintenance concerns within this area. The next slides that I'm gonna go through quickly are just going to be our Parker products that are specifically designed for these applications. So all these products can be found at the URL on the bottom left-hand side of these slides at www.parker.com/data center. So the first products that we're going to talk about are going to be two coolant tube offerings, so SB2P and PCT coolant tubes that we have. So SB2P is thermally formable, thin wall design tubing specifically made for this space, as well as use with single phase and two phase cooling. And PCT offering is going to be a product that we have a multi-layer polyamide offering with availability in PFA material as well. They are specifically designed for on-blade applications and perfect for all of these scenarios that we're discussing today. We also have on the left-hand side that you'll see here is all of our EPDM cured hoses. So along with the first two products that I mentioned here, these are all going to carry a UL94V0 flammability rating. It's very important in this space that's maximized, and all of the options that you're seeing here offer from Parker whether it be the server blade hose, the 62090 PDM hose, they're all going to meet that industry requirement out there and reduce the amount of concerns for flammability ratings. So we also offer custom manifold solutions that we have on the right side there. So high efficiency manifold solutions that are fully customizable for your specific application. And then we're going to move over to our liquid cooling cartridge from our Carstick line. So a fully integrated connection point that can be inserted into your cavities, including your cold plates. And on the right-hand side, you got an OCP designed quick disconnect coupling from Parker as well. So OCP-inspired design. It is specifically designed to reduce pressure drop and have superior energy efficiency within your system. The next slide is going to be our push button UQD. So a quick disconnect option there, easy to handle and operate, and it has a no spill quick disconnect option as well. So the final product that we have for today, again, all these products can be found on our URL at the bottom left, but the final product that we have is going to be the Sporlan QT-QD. So a quick thread dry brake coupling that's built off of decades of Parker Sporlan's refrigeration experience and is specifically designed for two-phase cooling in these areas. So I'll pass it off now to Yulin for some key takeaways, and we'll keep moving forward.
Turn off the camera. Here are going to be some. So yeah, essentially, the key of today's entire webinar is really about optimizing the thermal management for next generation data centers, with a particular focus on the liquid cooling for data centers and all of the components that play a very important role, for data center liquid cooling. So just to wrap up, so there are 4 key takeaways that we probably want to emphasize on. The first one would be the energy efficiency. So for new data centers, we're essentially looking at a PUE lower than 1.3, and for a lot of hyperscalers, the PUE might be even lower, like a 1.2 or even like a 1.1, etc. The energy efficiency, the improved energy efficiency can essentially requires enhanced thermal strategies to not only reduce the energy waste, but also extend the hardware life over time. And by the end of the day, when it comes to calculating the total cost of ownership, energy waste is pretty important, and also like the hardware life cycle is pretty important. All of those would contribute to the TCO. And from the technical perspective, pressure drop minimization is very critical. Optimizing tubing, fittings and manifold designs, and also the valves, like the Parker's mentioned just now. So all of those components are really important, because by the end of the day, they really just lead to lower pump energy and the compatibility of different components within a liquid cooled configuration in the data centers. So it's pretty important to select the right components in the first place. And in terms of the flow management optimization, so this is somehow similar to what I mentioned just now. So smart component selection, for example, low resistance tubing, UQD fittings, so they can cut the system pressure drop by up to 85%. And also simulation guided design prevents turbulent flow. Fluid dynamic simulation is required in the first place, which can ultimately improve the cooling reliability and also simplifies retrofitting. So from the cooling efficiency and the energy cost perspective, the transition from air cooling to liquid cooling to two-phase cooling, is the trend that we are seeing right now. And because the purpose is to manage the rising GPU thermal design powers up to 2,000 watts. And also two-phase direct-to-chip cooling reduces the flow rate needs by 80% with a lower maintenance and better thermal control. So we do believe that two-phase direct-to-chip cooling is a really promising technology moving forward. And finally, in terms of the future trends and the future-proofing technology, so AI-driven dynamic cooling and pressure monitoring is expected to rise, and also two-phase and refrigerant-based systems are gaining a lot of traction, despite the higher capex, particularly for hyperscale adoption. Because by the end of the day, people are calculating the total cost of ownership. So, capital cost is important, but if you're able to reduce a lot of operational cost by, adding a little bit more capital cost, then, that's still a good deal for a lot of hyperscalers. And by 2030, we believe that the liquid cooling component market size is going to triple, primarily driven by AI workload and also the retrofitting requirements. So with that, it comes to the end of the actual presentation. And yeah, so we're open to the questions.
Great. Thanks, everyone. That was really informative. And right on time. We have 10 more minutes for live Q&A here. So thank you for the compact management of all of that information in such a short space of time. Let me start off with a question related to leaks and reliability that a few people actually had. But we obviously understand that the products are designed for reliability and to be leak-free, but how do you assess the reliability of the products given the severity of leaks?
There are a lot of things. Go ahead.
Go ahead, Josh. Go ahead. You can start.
I was just going to say there are a lot of things that can be done internally, whether it's internal testing, third-party testing, and testing at the requirements of these systems is ideal. So we can do things like impulse testing. We can do secondary testing with compatibility between two different products or two different interfaces in a lot of cases. And push a cycle count to what we would say is an extreme in a short period of time to kind of test and place a reliability stamp on a lot of different products, if you will.
Yeah, I just wanted to build up on Josh. When you're looking at these components and you're trying to pick these components, a good idea is always to reach out to the manufacturer. There's a high likely chance that any scenario or any situation that you're trying to use one of these components that we have already done the testing for that. We've already tested our specific components in that scenario, and we can give you a lot of reliability data and testing on that specific case scenario. And when it comes to seal reliability, we do a lot of testing with all the seals that go into our components for every scenario that your system would be in. And we have a lot of data backing up our seal requirements are picking the correct seals. So whenever you're picking your components, depending on your system, depending on your fluid, you can ask us a lot about which seals to pick in which scenario.
Thanks to both of you. So let's maybe go from reliability to efficiency as well. This question is, how can the overall pressure drop be improved or mitigated within a liquid cooling system?
This is one that I kind of touched on a couple of different times. Using products, I probably said it 5 times during this presentation, but using products that are specifically designed for this space and to optimize the amount of flow that you have, as well as not impeding or reducing from a pressure drop standpoint is ideal. There are also a lot of things that you could take a look at in reducing the amount of connection points, using maybe specifically fluid transfer products that are designed for this space, in maybe a different method for installation as well, as far as optimizing the routings that you have are all pretty easy ways to improve the overall system efficiency that you have and reduce pressure drop within the system as a whole.
Great. Here's a couple of questions kind of correlated, I think, to do with the rack. So how will the rack manufacturing industry be affected with these new technologies, liquid cooling technologies? And why would you want to run PG25 in your rack? This person says they understand why it makes sense more externally, but within the rack.
So a lot of the rack manufacturers that we have seen when it comes to liquid cooling, the racks are going to have to adapt to the liquid cooling necessary equipment that needs to go into the rack. So all of the IT racks are going to be able to handle the manifolds that are going to be mounted to there. They're going to have space for the hose routings and everything. And there's a lot of systems where there's an in-rack CDU. So a lot of these racks for liquid cooled systems are going to be a little bigger than what you see for air-cooled systems, and they might be taller as well. But the capacity and the thermal capacity that you get from these racks is going to be a lot higher than what you get from an air-cooled server for the same space. So you're going to be able to do a lot more computing for the same space with a liquid-cooled server than what you're doing for an air-cooled server because of the higher thermal efficiency. And then the PG25 in the rack, the question with that PG25 in the rack, the PG25, the water itself will be taking the heat generated from the chip and be taking it outside. So the water itself will be the transfer media for that heat from the chip to outside of the building. So that's what the main feature for the PG25 and why it's in the rack itself.
Great. Here's a regional question, but maybe we can make it a little bit more generic. You guys talked about refrigerants. Are the refrigerants you listed allowed in California? I mean, I suspect that there's probably not just things in California, but around the world that may not be permitted.
So,
Can you talk about that?
So on that question, when you're looking at refrigerants, a lot of people I saw ask questions about PFAS, but one of the main important things to look at for refrigerants, whether it's allowed to be used in California or the rest of America or Europe and Asia, one of the main things you got to look at, especially starting at January 1st, 2025, is actually the GWP, the global warming potential number. And starting January 1st, 2025, in California and the rest of America and most of Europe, if a refrigerant has a GWP of above 750, if I remember correctly off the top of my head, if the GWP is above 750, you cannot use it. If the GWP is below, then you are free to use it. The PFAS regulations are not as clear right now, if I can remember off the top of my head, so I don't want to delve into that too much on the specifics, but right now the most important thing is whether you can use a refrigerant or not is a GWP number. And the refrigerants being used in pump two-phase refrigerants for direct-to-chip cooling all have a GWP of under 750. Most of them have a GWP very close to 1, the low-pressure refrigerants, and even the medium pressure refrigerants have a GWP that's close to 200 or 300. But on the refrigerant side, refrigerants are an engineered fluid. So there's a lot of companies out there that are doing a lot of work to come up with the best and most appropriate refrigerants to use so that you don't have to worry about the GWP and you don't have to worry about the PFAS as much as well. So I hope that answers the question.
Great. Another question sort of on mitigating reliability challenges here is from a hyperscaler perspective, given the cost of these racks, once deployed, there needs to be a way of minimizing the damage if there's a leak. What strategies are there to address those types of concerns?
There are a number of moisture sensing units that are being deployed in a lot of different areas, but this kind of ties back to the original concerns that we had in the maintenance related operations, as well as serviceability at a rack level, is using things like dry brake couplers in an area where maybe you're doing some sort of a maintenance concern. One, you're going to reduce the overall downtime that's associated with that one, because you're not cleaning something up within a rack level, but you're also reducing the amount of risk associated with an improperly connected product after you're doing some sort of a maintenance or a connection point that could potentially become a leak point. So if you're using something like a dry brake coupler in those areas, you're going to seal off on one end of that application to mitigate the amount of risk that you have to exposing the entire rack to a concern.
Yeah, I want to build up on Josh just a little bit on that. So on a single phase water glycol system, if you have if you were to have a leak, it is not necessary for all of the server blades to be connected in these systems for these systems to work. Even if you hot swap a server blade and you disconnect it at the dry break, you can take that server blade out and the rest of the system will keep working. It will keep pumping just like normal. So you'll be able to easily maintain and switch that cold blade that has a leak. On the other side, when you're using pump two-phase systems or refrigerant systems, you're not as much worried when there's a leak about electronic issues because refrigerant is dielectric, is not going to damage your electronics. But there's also mitigation systems and leak detection systems for both water glycol and refrigerants. They'll give you time to disconnect the server blade that's having an issue, and then the system is going to keep working just as usual, and then you can quickly fix that leak issue, and then connect it back. So,
great, thanks, guys. So we're at the bottom of the hour here. I want to thank everyone again for your time and trust in joining this OCP educational webinar. There were so many questions that we can't possibly get to them all, but as usual, we will provide Elvis, Josh, and Yulin the questions and your contact information. So if you have any last-minute questions, you can drop them in there now, and hopefully they'll contact you back. Otherwise, I want to make sure that we answer the question of where can you find more information about this within the OCP. This would be in the cooling environments project primarily. If you look in the data center facilities project, there are coolant distribution technology sub-project areas there as well. Some of this relates to sustainability and energy efficiency, which are in other parts of the community. But the cooling environments top-level project and its many sub-projects is one of the most active and engaged parts of our community with well over 1,000 engineers there. So stay tuned for more in that area at the Global Summit as that approaches. And again, thanks everyone very much for your time and trust. See you on a future OCP educational webinar.
Thank you, everyone. Have a great day.